So the last video was about half-wave rectifier basic circuit operation. Now let us analyze certain parameters about half-wave rectifier. So the first one we are going to consider is about average DC load current represented as IDC. So this value can be obtained by integration. That is, we are determining the area under the curve for one complete cycle for 0 to 2 pi, and then we divide it by the base value of 2 pi. So for a single area we are analyzing and then we are just integrating, so that is why we have represented as this value has been obtained by integration. So in equation wise we can represent the load current IL is equal to Im into sin omega t, which is for 0 less than or equal to omega t less than or equal to pi. That is, if we draw the sketch we will get in this way for 0 to pi and for 2 pi. So for 0 to pi we will have a positive half cycle over here. So this value will have a magnitude of Im, and since it is a sinusoidal waveform it is represented along with sin omega t. And for the second half of the condition, for that is for pi to 2 pi, we will have a value which is nothing but 0. So it is taken as 0 for this particular range. So this is the value of load current. So now to calculate the value of average DC load current IDC, we have to integrate with respect to the base, which is nothing but 2 pi. So this is done by integration. So integration is taken over here and the range of integration is taken for the limit from 0 to 2 pi. So 0 to 2 pi, what we are going to integrate is this load current ideal. So ideal in terms of d omega t, and we are dividing it by the base value, so 1 by 2 pi. Substituting the value of IL over here, it is nothing but Im sin omega t d omega t. So we saw about the different values for the different range of load current values. So for 0 to pi we have a standard value, and for pi to 2 pi it is 0. So we can split the integration in that way. So for 0 to pi it is Im sin omega t d omega t, plus from pi to 2 pi it is 0. So we can stop with that, and it is divided by 2 pi. So integrating the first half of the signals, that is from 0 to pi, we will have Im sin omega t d omega t. So if you integrate sin, we will get it as minus cos omega t, and the range of limit will be from 0 to pi. So we can take the value of Im outside the integration. So Im by 2 pi into, after taking the negative sign out, applying it as upper limit minus lower limit, we will get cos pi minus cos 0. So cos pi value is minus 1 and cos 0 is again 1. So minus 1 will be minus 1 which is minus 2, and we can divide that 2, and minus of minus will be plus. So the remaining value will be just Im divided by pi. So the average value of DC load current IDC is equal to Im by pi. This is the average value. So if you apply KVL to the complete circuit of half-wave rectifier, then we can get the value of Im as ESM divided by RF plus RL plus RS. So RF is the forward resistance which we take it for rectifying element, that is diode. RL refers to load resistance, and RS is nothing but the resistance of secondary winding. So in case when you are supposed to solve any problem based on this particular equation, you have to check for the value of RS. In case if RF is provided, you can use it directly in this formula, substitute for the different values, calculate Im and divide it by pi to get the value of average DC load current. And in case if it is not provided, you can simply neglect that and just apply the value of RF and RL along with ESM and calculate the value of required Im. So this is the average DC load current value. Second parameter, average DC load voltage EDC. So it is represented as product of average DC load current and load resistance. So DC load current we have calculated just now, which is nothing but IDL, and load resistance is RL. So multiplying the two things, we will get the required DC load voltage EDC. So IDC value, which is calculated as Im by pi into RL, and we know the value for what is Im also, which is ESM divided by RF plus RL plus RS into remaining pi into RL. So in this condition, the source resistance and the RF, that is the secondary winding resistance and forward resistance, will be very less than the load resistance value RL. So using this particular condition, we can further simplify the value of EDC as ESM divided by pi into RF plus RS divided by RL plus 1. So this ratio of RF plus RS divided by RL will be very less than the unity. So we can simply neglect that and further simplify the value as simply ESM divided by pi. So the DC load voltage is equal to maximum peak value of secondary winding ESM divided by pi. And for load current, that is average DC load current, it is IDC, which is equal to Im by pi. So this is the different values of DC load current and DC load voltage. So in case if you are supposed to solve any problems based on these two parameters, we have a small note for that. That is, do not calculate the value of EDC as ESM by pi directly whenever we have the finite value of RF and RS. So in the question, just look for the value of RF and RS. In case if you have a finite value of these two parameters, then you have to completely apply that in this particular equation and solve for the required value of EDC. So this is an important note. So we have seen RS and RF also. If it is not provided, you can simply neglect and use this particular relation. But if it is provided with a finite value, then you have to make sure that you use these equations.